Well, this is the wrap-up for Chapter 3, Differentials and Marginal Analysis. Boy, does that sound intriguing. Well, it sounds scary maybe, but it really isn't. It's all stuff you've done before. We're just putting it together. Differentials, you've actually been looking at these almost the entire semester. Remember that dx, dy? Dx and dy are differentials. We're going to use those differentials in economics to approximate revenue, cost, profit at certain levels. We're going to also find the differential of a function using differentiation formulas. It's really easy. Here we go. Differentials 101. All right. So you've seen this before. dy dx equals the limit as delta x approaches 0 of delta y over delta x. That means as the y values are changing, as it's going up or down, how does it go up or down when you change the x value by 1 unit, usually from left to right? Usually dx dy was just put together into one piece. But what you're going to see here is dy and dx can be separated. They can be thought of as a quotient. So we'll grab a pen here and we'll start rolling along. And of course, before we roll along here, notice, of course, if we're going to talk about dy dx, we can't have 0 in the denominator. We know better than that. So the definition of differentials, the differential of x dx, the differential of y dy. And since dy dx is the same thing as f prime of x, a small bit of algebra, and dy equals the derivative of x, or derivative of f, excuse me, times dx. Just multiply both sides by dx as if it were a regular number, which it sort of is. And another easy thing, if you're asked for dx or delta x, we're going to treat them as if they're the same thing. Any difference would be extremely small. Here's what the difference is. You have 2 points. There's point 1, there's point 2. Now imagine that you're traveling along this graph. So you're down here at the first point, called point 1 perhaps. As you go from point 1 to point 2, they're not at the same place, so there's going to be a difference in the x coordinates between those 2 points. That's delta x. In going from point 1 to point 2, there's also a difference in the y coordinates in getting from here to there. That difference is delta y. That's the exact difference between the two. Now what we're saying with the differentials is, first of all, if you want dx, you just take delta x. Real simple. Dy will be somewhat similar to delta y. And the closer point 1 and point 2 are to each other, the closer delta y and dy will be to each other. If you look at here, the difference between delta y and dy is very small. The further you get away, the bigger it is. If you get in here pretty close, you can basically use dy as delta y if you want to. They're almost exactly the same. So if you want to calculate the exact value of delta y, just find the y values at those 2 points and subtract them. Here's the y value for the second point minus the y value for the first point. That's it. Now, of course, you'll have to know what that particular function is. Maybe the function in that case, is x cubed plus x squared minus 3x plus 15, or whatever. You'll be given that. And if you want to find delta y, just put the 2 values of x in for this. You'll get one value for the first y value, another value for the second y value, subtract them, the second minus the first, and you'll have your delta y. Need an example? Well, let's go to it. Here's your picture. The tangent line is the approximation for applications of differentials. In other words, what it's saying is that if you really need to know this delta y, using dy is going to be close, and that'll be good enough. And it's much easier to calculate than calculating delta y. If you look back here for a second, look at all you had to do to get the y sub 2 and the y sub 1. Sometimes that can be a little bit tedious, to say the least, even with the electronic calculators. But it can be simplified if you just go ahead and use dy instead. So here's a function. You've seen this many, many, many times. Here's your function, x squared. You know that's a parabola, and because it's a positive here, you know it opens upward. If you didn't know that, you could take a second derivative, and that second derivative would be 2, which means it opens upward. How about that? We're putting everything together. Now it says find the value of dy when x equals 1 and dx equals 0.01. In other words, dx represents how far away are the 2x values. What that means is for 0.1, your x coordinate is 1. Real simple. It means for 0.2, your x coordinate is 1 plus a little bit extra, 0.01. There's your second x coordinate. And you'll put those values in that x squared. This one will give you y sub 1. This one will give you y sub 2. You'll subtract them, and that'll give you the exact value of delta y. However, you can shorten that a bit because you know calculus now. Take the derivative of f. You know that's 2x. And what you'll do is you'll write dy dx this way. Remember, where am I? There we go. Remember, that's our derivative, which can be written like this. And if we multiply both sides by dx, we can get dy by putting our x value in the derivative and then multiplying it by whatever we're using for dx. And dx in this case is, where am I? Come on. Where'd the pen go? There we go. Okay, so dy, we'll put the value of x in here. We'll put the value of dx that we have. So there's the 1. That's where we're starting. The 0.01 is how far away we're moving from the first point when we're talking about x coordinates. Just put those right in. Find the actual number. This is 2x, and the x is a 1. So this part becomes 2 times 1, or 2. And here's our dx, or delta x. Remember, delta x, for all purposes, are going to be the same. So that makes things simple. It's the delta y and the dy that'll be different. Not too much, but some. So there's your dy, which you can, for most purposes, assume that that's very close to the delta y. To find the delta y itself, put the value of the second x coordinate in here. Oops. This is a typo, by the way. I need to get rid of this. Slide 15. 15. Get rid of the S. Okay. And just put the numbers in. You almost don't need a calculator for that. You can see what you get. Notice that it's not quite the same as the dy we got before, but in most cases it's close enough for us. And that's much faster. There's something to be said for speed, right? Marginal analysis. Remember, we've talked about marginal things already. Marginal revenue, marginal cost, marginal profit. And remember, when we talked about those items, we said what we were talking about for marginals, whether it's marginal revenue or what it is, you're saying that x you're adding 1 to that. What happens to the y? If you increase the x value by 1, what happens to the y? Well, now you've got a simple way of doing this with a tiny bit of calculus. We're using economics, and you can check with some of the business instructors. They can tell you a little bit more. They don't use it a lot, but whenever you need it, you need it. So if you want marginal revenue, for example, you take the revenue at the second point minus the revenue at the first point, and if you want this delta R, and this seems a bit complicated to calculate, you can approximate it and get very close just by using dr, a differential instead. So what you'll do is you'll find dr dx, put your x value in, multiply it times your dx, which in some cases will be a 1, and you find out how the revenue is changing if you change the demand by this amount. That's what it all means. And the calculus makes it much easier. Remember, what we talked about before was one additional unit. X moves up to x plus 1. By the same token, you can use DC and DP for the differential for cost and the differential for product. It works exactly the same way. So once you've got 1 down, you've got 3 automatically. So here's an example. We've got profit. We all like profit, right? And there's our function. And if we were mathematicians, we'd be a little bit obsessed with maybe about writing it as a function of x. We've got our function now, 0.0002 x cubed plus 10x. If we want to find out how much the profit changes when we go from a demand of 50 units, selling 50 units to 51, how does the profit change? dP. The exact value we want is called delta P. dP is almost exactly the same. That's what we can get by using calculus. This is what we get by using arithmetic. And this, the dP, is much faster to get. So one last note on this slide. This would be the x value, and this would be your delta x value because one more. So your x value is being bumped up by 1. X is where you're starting. dx is how much you're moving away from that initial number. So a little bit of differentiation. If you need to look back here for a second, yes, differentiate that, and there you go. dP dx, you got it. And then the next step, after you differentiate, all you have to do is multiply both sides by dx. Yes, it is that easy. dP equals dP dx times dx. That makes sense. If you look at the equation down at the bottom, if you cancel the x's, you'd have dP equals dP. Of course it makes sense. So here's our expression for dP, which will be a good approximation of the delta P, the exact value. Just put the starting number in for x. This is the initial demand value. This is how much we're increasing the demand or the sales. And this is how it's going to affect the profit. You'll get another $11.50 by jumping your sales from 50 to 51 units. Just let the calculator do the work after you've done the calculus work. Very simple. $11.53 is how much it would be exactly. That's your delta P. Looking back here a second. Oops. That is your dP, what you get from the calculus. This is what you get from the arithmetic. Close enough in most cases that you're not going to be concerned about the difference between the two. There's a visual of what you've got in going from this level of production at 50 units to 51 units is an increase of 1 unit, 1 unit more. We've talked about that for marginals. When that is increased by 1, how far up does the profit go? In this case, about $11.50, or exactly $11.53. Formulas for differentials. We'll see in a number. Most of these should look pretty good because these are all differentiation rules. The only thing that's different is in this first one, for example. This is like the derivative cu with respect to u is c. That's what this really is. the derivative of something times a function equals, well, you can see it for yourself. All they did in going from this, which is an old rule that you've used, to this is just multiplying both sides by du, and you got the same thing. So you don't need to memorize these. You can just take your differentiation rules and multiply what's on the bottom of your derivative, which is what you're taking the derivative with respect to, like dy dx, multiply both sides by dx. Try about 2 or 3 of them, all of a sudden you'll feel like you're an old hand at this. So, let's take a look at some examples. Here we've got y equals f of x. And what you'll do is you'll take the derivative. Remember that f of x was x squared. So there's your derivative. And to get the differential, multiply both sides by dx. And there you've got your differential equation. Function to the derivative to the differential. So what you might want to do in your notes is make a note that actually represented an x squared, and I'm going to make a note to myself too. Slide 37 and up needs an x squared. So for this next one, you have 3x plus 2 over 5. Take the derivative. Remember, you do a rewrite there. 3x over 5 plus 2 over 5, and then take the derivative. And then multiply both sides by dx. And there's your differential. Take the derivative, multiply what is on the bottom of your derivative. There's another function. Take the derivative, multiply both sides by dx, and there's your differential function. Function, remember you're going to rewrite that thing, at least I would anyway. I'd make it 1x to the negative 1. If you want to use the quotient rule, go ahead. Not I, said the pig. And there's the derivative, and then multiply both sides by dx, and there you got the differential. And that's all, folks. Any questions? Send them to me. But it's pretty easy. We're just putting some things together and making things easier. Remember, dy dx is the derivative, dy is the differential. Dx and delta x are the same thing. Delta y and dy are not the same. Delta y is an exact value. Dy is a good approximation by using our calculus. And that's all. See you next time in, we're moving to a test in Chapter 4. See you later. Keep smiling.